Okay, so welcome everyone to Paper Club. Today, Amin is going to be speaking to us about graph attention networks, and this should be very interesting. This is a topic that interests us at NPAN, and hopefully we'll have an interesting discussion about it. Go for it.
Thanks, Carlos. So let me share my screen. Sorry, just a moment. I have to. I'm having some issues with sharing my screen because of permissions.
It's working.
It's working now. Okay, great. All right. Sorry about that. Okay, can everyone see that fine?
Yep.
Okay, let's start. So graph attention networks. So let's talk about, first of all, the motivation behind graph attention networks. So the central idea. So the main takeaway that I got from it is that the goal is to create a convolution operator on a graph which retains some desirable properties that are present in the original convolution operator applied to images, with some extra properties as well. So we'll talk about what those are and then how they are actually satisfied in the GAT. So I think we've talked a few times about GNNs and attention mechanisms. So I think I will kind of give a quick overview of GNNs and convolutions on graphs, and then we can jump straight into the model. So so the GNN, when it was introduced, the whole idea is we want to get a representation of each node, or a representation of the graph through that, which encodes information about how the nodes on a graph relate to each other. And so I think the first GNN, how this was done was, so through an iterative process, you aggregate information from your neighbors. So the nodes will have feature vectors, and the edges can have feature vectors too. And then, so in this way, information is propagated across the graph, and this is repeated until the node states reach some equilibrium. And then this is, so then these representations are then used downstream for whichever task. So there's in a simple case, a neural network is shared across nodes, and then there's a softmax over a number of classes. So for a classification case, for example, and then training happens in the usual way. So the issue with this, I guess, as it pertains to this paper, is that, well, first of all, a propagation function like that, which reaches an equilibrium, relies on some assumptions. So I think actually they use in this paper in 2005, they use the Banach fixed point theorem. So it relies on it relies on assumptions that aren't generally satisfied. And another issue is that it could be expensive to compute this equilibrium state. I guess it depends how you would define convergence in that case. Okay, so that's the original GNN. They talk about how so it's improved by using gated recurrent units during the propagation step. They talk about convolutions and graph convolutions on graphs. So these can generally be split into spectral and non-spectral approaches. So for example, in the spectral approach, you would use you would take the Laplacian of the graph and find the eigen decomposition. And so in this way, the operation is defined in the Fourier domain. But one of the issues with this, and after this there are different approximations which can be applied to improve the model. But after the issue with this is that it is I saw a phrase in a different paper which said basis independent. So because the Laplacian can be used as a way to describe the graph, if we were to train a model on a graph and then we want to apply it to a different graph, well, the Laplacian isn't the same. And so if you learn a filter on one graph, it can't be applied to another one as easily. Okay, I think I will jump straight to the model. So how it works is, so the setup is each node has a feature vector, and we want to produce a generalized a representation of the node. I think before going into the model, I want to actually take a step back and talk about something that I forgot, which is the properties that we would want this layer to have. So if you think of a convolutional layer on an image, it has some number of properties. For example, the number of parameters of the layer is fixed, independent on the image size. So if you were to, so it depends on the kernel size, which is passed over the image instead of the image size. We would want something similar for graphs. Another property is localization. So have it, I'm not sure where they have it, but we would like, at each layer, we would like the node to learn about its neighboring nodes only, and to be localized in this way, in the same way that a pixel sees its neighboring pixels only inside the kernel. Another one is we want the layer as applied to a node to be able to assign importances to its neighbors in a way which is not fixed beforehand, in a way which is learned. So, and the final property is we want it to be used, we want to be able to train a model on a graph and then apply it and test it on a graph which has never been seen before. So it doesn't matter the actual graph structure. We can train a model on one structure and test it on another one, and this is actually done in the experiments, which we'll get to after. So those are some of the properties we ideally would want to have the convolution layer applied to graphs to have. So we'll go through the model, and then we can talk about how these are satisfied. So okay, so each node of the graph has a feature vector, and the goal is we want to apply self-attention to the nodes on the network. And so what actually happens is, first of all, the feature vectors for each node are linearly transformed to the desired output dimension of the layer. And then these feature vectors of a different or the same dimension, you then take every pair of nodes and you compute the attention coefficients, and so yeah, so these are the attention coefficients. Now, if we were to just apply self-attention over all of the nodes on the network, so respective to one node, apply self-attention to all other nodes, then we would lose all structure. And so the way that the graph structure is included in this model is by applying masked self-attention. So each node is only allowed to attend to its direct neighbors and no other nodes on the network. So this actually satisfies the localization property automatically, just by definition of the model. Okay, so yeah, so in the usual way, the attention weights are normalized by taking a softmax over the coefficients. So this is a softmax over the neighbors of the node of interest. And then these are so these values are then used to these values are then used to compute the attention weights. Were there any questions at this point? I forgot to ask.
I'm following.
So I do have a question, and that is, and I probably missed it. So we're still at a node by node level, and that we're only looking at each node at its in turn, and we're not looking at a node's neighbors yet. We haven't got into the convolution where we'll look at the node and its neighbors. Is that correct?
So for the layer, you can think of the layer being applied to each node independently. Yes. And at the layer, the node considers its neighbors only. So the goal is you have an input representation for the node, and then you want an output representation which aggregates the neighbors' feature vectors in some.
Yes, and so we can deal with a variable number of neighbors. Okay. Yeah.
Right.
Yeah. Thank you. I understand.
You're welcome. Thanks for the question. So, okay, I'm not sure where to go off now. Let's see. Okay, let's talk about the attention mechanism that's used in this paper. So there's no query key and value matrices. It's quite simple. So the input representations are projected, are linearly transformed, and then they are then concatenated with the same transformed vector for the neighboring node of interest. And then there's just a simple feed forward network followed by a leaky value nonlinearity, and so there's a visualization of this here. So this is how this describes the attention mechanism, and so we can talk about how one of the other properties is satisfied, which is the ability of it to be applied to unseen graphs. So because this is an edgewise mechanism, so if we so we're considering every pair of nodes, of course within a neighborhood, then you can see how this can be applied to unseen graphs, because we only care about in terms of attention, we care about pairs of nodes, and so as opposed to the graph structure as a whole. Okay, so this is the attention mechanism to get the coefficients, and then they are then normalized to get the attention weights. And so the output representation is then just a weighted combination of the transformed vectors for each of the neighbors, and then a nonlinearity is then performed. So I think in the paper they use the leaky ReLU and also the exponential linear unit as well. Okay, so in terms of the experiments, what they did was multi-head self-attention. So what happens here is so that the attention mechanism is repeated independently some number of times, and then the output vectors are then concatenated to get the final multi-head output for the layer. There is actually a difference in the output layer when dealing with the final layer of the network. So if you're dealing with a classification problem, you would want your final output vector to have dimension as the same number of classes. And so concatenating vectors doesn't make sense because, well, yeah, as it says here, so if you have k heads and f dash features, then you would have this many features for each, this many output features for each node. And so instead what happens is aggregation, instead of being done by concatenating over the heads, is done by averaging over the heads. And then, so here's the average, and then the nonlinearity is applied afterwards. So this, yeah, as it says here, this would be a softmax or sigmoid for classification problems. So
sorry, it's just that I found this a bit confusing. So they are, because normally if you have your softmax layer, there's a matrix before the before applying the nonlinearity that is able to reduce the dimension to the number of classes.
Right.
So you have your logits, right? I don't really understand why they don't do that. Like why do they need to average the?
So you mean why don't they just concatenate it and then just project it onto the number of dimensions you want?
Yep. With learnable weights.
I'm not sure, actually. I'm not sure why that way was used. I think maybe they only wanted one matrix of parameters, so that the linear transformation is just done once. I think that could be why, but yeah, I'm also not convinced.
Okay.
Do you have any idea why?
No, not really, because, well, in principle, especially when you start trying to like do more and more attention layers, or in general when you're doing attention layers, typically they, or at least, so in most of the papers that we have seen, when they either concatenate or so when they try to reduce like by averaging or adding versus putting just a learnable set of weights, usually it's worse performance wise.
Is it some form of ensembling? Because typically would expect every head to learn something different, whereas here we kind of then expect that every head sort of learns the same thing, because otherwise why would you average them? And so maybe it's a sort of ensembling technique to reduce noise, perhaps?
I think each head does learn something different. And
yeah,
but then if they would be different, you wouldn't add them, right? But here they add them and average over them, so you kind of would expect their outputs to be somewhat aligned.
Right. So you mean this? It wouldn't work with. So when you say different, do you mean a different number of dimensions for the output of each head, or?
No, generally trying to capture something different about the problem, right? So
Right.
I remember when we had the image ones, right? So we had, if I remember correctly, that the different heads had essentially different convolutional kernels in that particular problem. Now, but of course, when you concatenate them, that's fine because you just add the information together. But when you average over them, you kind of enforce that every head kind of gets the same pressure in conforming to the right output. So it seems that they would learn to be the same or at least similar, and any noise between them gets averaged out. So it's, yeah, you wouldn't, there shouldn't be a fundamental difference between one head and multiple heads if all you do is averaging over them. I think so, but there might be some other reason.
It's probably a bit of a chicken and egg situation where because you're using averaging, you are forcing the heads to learn similar representations. Because you're basically ignoring the heads that learn something wildly different. Whereas if you concatenate, you're in a way forcing them to learn different, look at different aspects of the problem, and then the next layer puts a weight on those learned representations. Anyway, it's an interesting choice.
In the same way, how like the average of a concatenation also wouldn't make sense, right? Because it would completely destroy the purpose of a concatenation. So I would guess almost it's a problem of how much how big the matrices should be, and so it might be just a simple reduction technique. I don't know.
Yeah.
So to go off that point, they describe the use of like multiple heads in the paper as regularization. So maybe the goal is to compute similar representations across the heads, and then average them as a way to I guess not rely on any single one. So it's a regularizer.
I wonder whether the variance across the heads would tell you something about internal uncertainty about the problem. That might be interesting, right? If you ask the model how certain it is about something.
Yeah, I think that'll be interesting.
Yeah, that's an ensembling technique, right? You look at the ensemble variance, and it tells you whether the model is uncertain. So it's a good indication of epistemic uncertainty, right?
Yeah.
Which is nice. Okay, cool.
All right, thank you. So just one more point about the model, just I guess to summarize, is that this is just a weighted combination of the transformed inputs, and so they say that in previous models this is either given as fixed, so as edge weights, or it's just included as a learnable parameter. But in this model, instead of the value being included explicitly, it's included implicitly through the attention mechanism. So that's a summary of the model, I guess. Okay. So were there any other questions at that point? Okay. So which property, we talked about localization, we talked about a fixed number of parameters. So as I just described, the weighting of the neighborhood, the neighbors is learned, and so the assigning of importances to neighbors is another property which is satisfied here. A good thing about the model is that because attention is edgewise, as I mentioned earlier, you can parallelize this operation over the edges, and because computing the output features for each node is shared across it can be parallelized across all of the nodes, and yeah, so as it says, as opposed to the original GCNs and the variations, there are no eigendecompositions and other operations which don't scale linearly in the number of vertices and edges. So I actually had a question about the model, which was, how can you include edge information? So it actually says at the bottom in the conclusion that you can't. So if you have any edge features or edge weights which you think would be good to include in the model, some important information about the problem, this isn't included in this model, but it can be readily applied to directed graphs. So in that case, you just mask. So in the directed setting, you would just mask some extra nodes, and yeah. So and in terms of implementation, your adjacency matrix it just wouldn't be symmetric in that case. So okay, I'm not sure there was anything else in this part. Okay, I think we should be good to go on to the experiments section. So the data sets that they use to evaluate the model, there are 3 citation networks and 1 protein-protein interaction network, and they test it for 2 different types of problems. So in transductive and inductive. So the difference between those in the graph learning setting is that so for transductive learning, at training and inference time, you're operating on the same graph, and so there's only one graph, and you have some number of training nodes, some number of validation nodes, and testing, as it says here, but of course, every node has feature vectors, and every node can see the feature vectors of the neighbors. So that's transductive. Inductive is the case where at inference time, you might see a different graph structure than at training time. And so this is what is used in the protein-protein interaction data set. They have, they have 24 different graphs, and 20 are used for training.
Yeah, sorry, there's a comment on the topic from before, which is that can you transform any graph with features on edges into an equivalent graph with additional nodes to represent the edges and featureless edges?
Well, I'm not sure I understand the question.
So the question is if because they say that you cannot add edge features to the graph, to the graph attention network. But what they are proposing is, well, instead of trying to add an edge between 2 nodes, you add another node which contains the features that you would give to the edge.
Oh.
So, well, I mean, I haven't worked too much with graph networks. I don't know what that means for the adjacency matrix. I don't know if it will become prohibitively large, especially because you have to make this. So typically you do anything that involves the adjacency matrix, you try to do it in a single go. So I'm not sure if that would work, but it's an interesting idea.
Yeah, so it would cause an explosion in the number of nodes. And what would you do with the nodes which are on which are kind of between the edges? Would those be would you want representations of those, or would you just want to use them? I'm not sure.
Adam, I don't know if you want to make a further comment about it.
No, I just wanted to, sorry, this is Adam. I was just thinking about whether that was really excluding the edge case. And it seemed like you could create an equivalent graph or an isomorphic graph in some sense by introducing new nodes corresponding to the edges. It wouldn't explode the number of nodes. It would, if the edges were just between two nodes, it would add one sort of pseudo node for every edge. So that might or might not be too substantial in the kinds of use cases they showed in the experimental results. They had quite a small number of edges per node on average, something like 2. But as I mentioned in the chat as well, it looks like they are working with proper data sets and are actually on the Open Graph benchmark leaderboard for pretty much all of the sample problems.
Yeah, I think that's an interesting idea. I'm sure, given the huge number of citations, that's possibly something like that has been tried, or at least that this model has been extended to include more edge information than just directed and undirectedness. Yeah, but thank you. Okay, so all right, so these are the data sets. Something which is interesting. This is actually a question that I had as well, which is that there are a small number of training nodes compared to validation and testing, and I think in this paper it's clear that they wanted to match the splits used for benchmarking in other papers. But I was thinking in the first place, why is the split like this anyway? Is it because graph models don't need a large amount of training data, and so this is what is used for benchmarking? Or is it that in most problems where you might deal with graph data, there's a lack of labels, and so you would want the model to perform well on a small fraction of training nodes? I just thought that's quite interesting, because otherwise it's the split is kind of the other way around.
I wonder if somebody who knows this literature much better than I do, because I know I'm totally unfamiliar with the graph learning literature. If you can train something with such a small number of examples, one tends to think that it's a fairly simple problem. And if some of these problems look like they're node classification problems, so basically you're classifying a node which represents a paper, and the content of the node basically is an embedding of its abstract, and you're trying to label it by subject. And it suggests to me that actually that's a fairly sufficient bit of information to do the labeling. And You know, I may be completely wrong about that. So I'd be interested if somebody knows these benchmarking problems a little bit better. And they, of course, they just reference them. They didn't actually describe the tasks or say very much about them in this paper.
I think it's also, if you see that the number of training nodes is always 20 times the number of classes. So they're probably taking 20 examples per class and hoping that that's enough for training and then testing on everything that's left. I think it's more motivated by what Amin said, which is that you would like it to learn from as little of the graph as possible so that you can infer stuff on the remaining graph. Which is a very interesting property of these graph models. They tend to be either semi-supervised or very minimally supervised.
Right. Yep. Thank you. So what do we need to say here? Okay. Okay, so for the protein-protein interaction, we're dealing with a multi-label classification problem, and so yeah, each node can have several labels. Okay, so in terms of the data set setup, I think this is fine. So yeah, a number of different methods are used to baseline the model, including just a standard MLP. So just kind of forgetting about all graph structure and trying to classify nodes as just feature vectors by themselves. So for the experimental setup, so for as it says, for transductive learning, they use two layers in the GAT model. They have 8 attention heads. Exponential linear unit is used as the nonlinearity. So for regularization, they apply L2 standard L2 regularization, but something which was interesting, they also include dropout. So essentially, what this does is at training time, each node receives information from a randomly sampled neighborhood instead of the entire neighborhood, and so you can see why this is regularization. They mention, I believe it is the graph stage method. If somebody knows about this model more than me, please let me know. But in this model, at training time before aggregation of neighborhood information, a fixed size neighborhood is sampled instead of it being well, yeah. So it's yeah. Instead of it being a probability of each node in the neighborhood, it's just a fixed size. And so you can see how this model, because it doesn't specify any size of a neighborhood, the model capacity is larger, because it doesn't matter how many neighbors the node has, learning can still be done well. So okay, another interesting thing, and I think this pertains to the use of the model in inductive settings as well, is that the model is trained on the core data set and then just reused on the site CO1. So I think that's pretty cool. For the PubMed data set, there are they changed the model. So instead of having one attention head in the output as was applied to the other data sets, they keep 8, and they strengthen regularization. So just basically more regularization. Okay, so for inductive learning is similar. Instead, they use 3 layers instead of 2, and they say they don't apply any. They don't need to apply regularization because of the size of the graphs, or rather the size of the training set. And I think there's also another point about as a benchmark for the inductive case, they test against the same model, but where the attention weights are just set to 1. And so this kind of mimics a model which doesn't assign importances to neighbors. Okay, so in terms of results, I'm not sure what there is to say. Did anybody have questions or comments from this point?
So, I mean, it's interesting. I think it's interesting how they put the experimental setup, because I imagine that they tried a whole bunch of hyperparameters, and I haven't looked. There's no appendix here, but as usual, it's interesting to see an ablation study, right? I don't know. We have spoken several times here about calibration, and here they are optimizing for accuracy, right? Which I'm not saying it's the case, but so what we typically see is that optimizing for accuracy results in huge miscalibration. So I don't know. I think that there is a bit missing here to understand. Well, if you relax a bit regularization, maybe you can get a different set of results. But yeah, otherwise the training seems fairly standard. Like they use Adam.
Yeah.
It's yeah, it seems like they almost make it look like you could be able to do this off the shelf. Just put a few layers on top of an adjacency matrix, and that's it.
Right.
Which is interesting, I think.
Yeah, I think that is interesting. How you can, seems like you can just take any graph and just apply it. Just take a pre-trained gap and you're good to go.
Yeah, and I like that they don't use like some very convoluted training mechanism, like you know, like sometimes you see that they train on one part of the graph and then they change for another part of the graph or something like that. Here it's just normal training, which in my opinion gives a bit more validity to their results, right? That they didn't have to do any weird tricks so that the thing could learn. And I don't know, I see that as that puts more power on the fact that they use few nodes to train and then get state-of-the-art performance, because it's not just that they use few nodes, but they use few nodes and just a normal training algorithm, which is nice. Right.
Yeah, I think in general, yeah, the model is quite simple. I think I was interested by also the fact that for the attention mechanism, they used just a single neural network layer with concatenating the feature vectors, and nothing else. So that's interesting.
Mm-hmm.
Okay, I mean, let's see. I'm not sure if I missed anything. I think there is a point that they make about interpretability. So it would be nice to see this work extended to kind of use the attention weights to interpret or explain predictions. And in fact, they do this kind of qualitative analysis. So basically, they take the first layer of a pre-trained model on Quora, and they project it using TSNE, and you can see that the nodes in each class cluster quite well, and they also show the attention weights between pairs of nodes so the thicker the edge, the bigger the normalized attention coefficients. So in terms of interpretability from this graph, I'm not sure what to take away from it, but I think that could be very interesting for possibly explainability as well. Okay, were there any questions, comments about the paper?
I had one very small one. I noticed they changed the activation function from leaky relu in the discussion in the beginning to ilu in the discussion of the examples, the benchmarks. I don't know, is that interesting for any reason? Was there a reason that they had to make that change?
I think probably because it gave better results. I'm not sure why they chose this nonlinearity in particular. They don't mention why there was a switch.
Yeah, I didn't see one either. Yeah, that's kind of, whenever there's something like that where there's a difference between the kind of the mathematical introduction and the implementation that's not commented on, it always kind of raises a, it's not a flag, it's just a question, why did they have to do that?
Right. It seems like it was, it's just because of better performance, I would assume. So.
This is the first paper I've seen on networks and neural networks on graphs. Have other people had much experience with other papers and other research in this area?
Do you mean papers presented at Paper Club or
Paper Club or elsewhere on graphs and neural networks?
So we've presented quite a few graph-based models and architectures. I'm not sure how many, at least 3 or 4, most likely more. And in terms of in the literature you were asking, it seems.
I was just asking, generally people's experience, because I've got an observation, but it's a uneducated one, and that is that a lot of data sets could be transformed into a graph. So we could take the MNIST data set, for example, convert it into a set of graphs, and then try a technique like this on it to compare it against the techniques that we know work well. Has anyone seen that approach or an approach like that?
I think I vaguely remember seeing a KNN, K nearest neighbor MNIST data set. But okay. Do you know how that would be, how exactly that would be made into a graph format?
well, I don't, but just thinking off the top of my head, on one level, you can say every pixel has neighbors of every surrounding pixel, but that doesn't, as this only classifies on a node by node basis, that won't get you very far. So you sort of need a node that represents each image, which it could have the neighbors of all the pixels in it. And then those nodes that represent images can then be connected. And then you might be able to, reformat the MNIST dataset in such a way that this approach could be applied to it. And so when you're classifying a node in this approach, what you're really doing is the equivalent of classifying an image inside MNIST, because all the neighbors of that node are the pixels in that image. My expectation would be that this, we would lose something in this. It wouldn't work as well, but it took me a long time to work through why.
Yeah, I think that's yeah. There's a lot of flexibility with these approaches. I don't want to guess how the KNN MNIST dataset is created. But yeah.
Well, thank you. I'll look it up. So thank you.
Yeah. Thanks. I will also look it up. I think we have a point here. Oh, this is thanks. Was there a question?
Yeah, we just got a question. Can you see the questions, Amin, or no?
No, I can't get them.
Yeah. So the question is, can we implement 2D node features instead of 1D? For example, if the node features are word embeddings in Cora dataset, they only use bag of words as node features.
So 2D node features. So as in images.
Or I guess a sentence, right? So if you have a sentence, each node would be like embedding size and sequence length.
Right. So would you know, Carlos? I'm not sure why you wouldn't just flatten it and make it one vector if you want to in that case.
So for the case of images, I think it's simpler because the 2D you can flatten the 2D vector and it's fine. Right. In the case of sentences, what we would have to check how all the matrix operations are made. But there is a chance that you might need to specify your sequence length at some point so that the dimensions are always consistent in all the matrix multiplications. But yeah, otherwise I don't see why. I mean, it should be simple enough to propagate the matrix operation along one dimension or even several dimensions.
Right. It would, yes. But thanks for the question. We've got another question here, I think. Oh no, this is Adam recommending a paper.
Honestly, I won't go so far as to say I'm recommending it, but this kind of follows from my comment earlier, which is basically question on this particular problem category. They don't seem to be really leveraging much from the graph, and possibly. And that just I noticed that I was looking at the leaderboard and noticed a couple of outliers in terms of the numbers of parameters. So some were in tens of millions of parameters, a couple were in tens of thousands of parameters, and I thought this was one that looked kind of interesting. This paper basically saying a pretty simple method outperforms graph networks on some categories of problems. I've not looked at the paper, so I don't know how strong a claim that is. And I'll also note that it came out early summer, and a lot of folks have subsequently posted slightly better results using graph neural networks techniques, but it's, you know, it's 1 or 2%. It's not 10%. And I think the simpler method, you know, was probably quite compelling midsummer.
Yeah, well, yeah, thanks for sharing the paper. I think it is interesting that methods which don't include graph structure at all could be used on some data sets to beat ones which do. I think there's actually an example here where the standard MLP beats deep walk, and so on the PubMed citation network. So I guess that's an extreme example.
Great, cool. So we've run out of time for today. Thank you, Amin, for the presentation and the very interesting discussion. Thanks everyone who participated in the discussion and made questions and made comments in the chat. So we have, for a while, we've been doing this series about attention mechanisms and transformers. To be honest, we are running out of papers to present on this topic, so it is possible that next week it's not going to be attention. We'll try to find something, but we don't guarantee anything. What we would really appreciate is that if someone wants a paper presented or wants to lead a discussion, please do write to us. The idea is that we have a variety of ideas in the paper club. So please do send your suggestions or just present a paper yourselves. As usual, it's not necessarily a presentation, just something to start a discussion. Otherwise, thanks again, Amin, and thanks everyone who joined us. See you next week.
Thank you very much.
Thanks, everyone.